Hello and welcome to another Math question, Math 2010 question 2. So let's get going. Okay, first it says square both sides to prove that this result is true. Let's do it. A root 2 plus b squared is going to be 3c squared. Multiply it out, you get 2a squared plus 2 root 2 ab plus b squared, and that equals 3c squared. Okay, right. Now we want to make sure that we get the right kind of answer here. I mean, immediately in my head, I'm thinking I've got an irrational term there, and that's an integer, and that's an integer, and that's an integer. That just doesn't make any sense. You know, that's not possible. For example, right? You could say then you could work out what root 2 was here. You could say it's 3c squared minus b squared minus 2a squared over 2ab, and that implies that root 2 is rational. Yeah. In other words, this root 2 term. This root 2 term must be 0, as otherwise root 2 is rational. Well, appears to be rational. Why does it appear to me rational? As I can write it as a ratio. How about that? I can write it as a fraction, in other words, as I can write it as a ratio. Yeah, that's clearly nonsense. Okay, so if that term's 0, then either a equals 0, in which case we're going to get 0 there, 0 there. We're going to get b squared is 3c squared. So b is root 3c, but then all of a sudden root 3 appears to be rational. Yeah, this appears to suggest root 3 is irrational. Sorry, is rational. Unless b equals 0. Yeah, now this looks a bit dodgy because it almost looks like c equals 0, you got division by 0. But look back up at this sign. It was just a, we were looking specifically in the case where b and c were not non-zero values. And if b is 0, c must be 0. Just look back at the original top equation. Okay, so there we go. Or b equals 0, and a very similar result here because you're going to get, what are you going to get? B equals 0, you're going to get 2a squared is 3c squared. Okay, so let's have a over c is root 2 over 3. They've already told me that I can assume that that is irrational, and so false by the same reasoning, and therefore a equals 0, and therefore z equals 0. In a similar reasoning, this is false unless a equals 0, c equals 0. So a equals b equals c equals 0. Done. Next part. Right. Suppose now that mn are integers, such that the distance from the point little n to that is the distance from the point big N to that. Well, it's a weird question, isn't it? It's saying, like, show that the distance, if a point is a certain distance from a given point, show that there's only that point, which is that distance, no other integer point as well. They're integers. I guess what we're going to have to do here is the old, multiply out. Now, you need a fair bit of space for this because it's just like a bit of an algebraic nightmare. Okay, so we're going to get m minus root 2 squared plus n minus root 3 all squared equals capital M minus root 2 squared plus capital N minus root 2 root 3 squared. Okay, write out what we got. We're going to have m squared minus, this is going to be tedious, isn't it? 2 root 2 m plus 2 plus n squared minus 2 root 3 n plus 3. On the other side, it's practically identical, just with capital letters. Oh, missed an M there. Oh, come on. Good. Right, now we can cancel. And now we can look, it never hurts to look back and reflect on what you've done. Look at what we just had. We had root 2s and root 3s, and we showed that if you've got a number times root 2 plus a number equals a number times root 3, and those numbers are supposed to be integers, well, there's only one conclusion to draw, and that's they're all 0. we're obviously going to use this because we've got root 2 terms, root 3 terms, and integers because n, m, n, m, n are integers. So we just got to really shove it into that format. I'd probably do it something like this, make it super obvious, you know what you're doing, by just going, okay, well, I'll have the root 2's, and that will be 2 capital M minus 2 little m. Then you've got the integers, which is our m squared plus n squared minus m squared minus n squared, and that equals the root 3's. Well, I can put that over here, my root 3's. Oh, look, that should be a root 3, shouldn't it? So I'm going to have a root 3 times by 2 little n plus, no, let me get this right. No, I'm leaving it on that side, so sorry. Yeah, because I'm going to be moving that over. I think that's right, and that's all done. I think that's correct. And now we can easily argue from 1, yeah, let's just make it real clear where we're getting this. 2m minus, oh, that's supposed to be another m, isn't it? Yeah. 2 capital M. I hate the way they got you to use capital M and little m in the same question here. That's really not a good idea. Okay, so we get that, and then from this one, you know, from the fact that C was 0 in the original result, you know what I mean, the original result, I'm talking about this original result. C is 0 as well there, so I'm just using that, and I get straight away n equals m. Well, there's a surprise. Okay, so it seems like a real non-event, that question, but, you know, like all these things, if they've got you to do that, it's going to come up later on, and it does. Okay, part 3, they give you this function, which basically gives you like a point and the distance from that point, and you've got to count how many integers are, you know, within that given distance. In other words, you know, you've got a growing circle here where r, as you increase r, the circle grows. A and b is the center of the circle, like it is in their example, and the answer to this function is it counts how many points are in the circle. So it's quite an interesting little question, really. And they've said, explain why n 0.5 0.5r is a multiple of 4 for any value of r. Okay, you know, this isn't hard to see actually. If we just go straight to GeoGebra, like here's something I drew earlier. Basically, I'm gonna vary the circle. Let me just change this into slightly nicer looking lines. Yeah, cool. And the same for you. Cool. Okay, so what I can do here, firstly, I just wanted to show you what this does. Like the reason why we're always going to get multiples of 4 here is because you've essentially got 4 identical quadrants, yeah? They've got reflective symmetry in the line x equals a half, y equals a half. Like for all of the lattice points, you know, you take this lattice point here, it has its equivalent being reflected in the line x equals a half, then being reflected in the line y equals a half, and then being reflected again in a line x equals a half, and then if you did it again in y equals a half, you get back to where you started. We've got this lovely symmetry there, you know, for all of the points on the lattice, and that's why as the circle grows, oh, that's annoying. I was hoping I'd be able to change the radius of that there. Let me try again. Let's just get rid of this. Cool. And get rid of that. And we'll do the circle again. But I just wanted to very quickly show you what we've got here. So, you know, 4 points. Then we hit 8 points all at once, you know, but, you know, there's no way we can hit a point in the top right quadrant and not hit a point, 3 other points, each within their own quadrant, yeah, because you're going to have perfect symmetry there as the circle grows. And so that's going to be my argument, basically. But, you know, the devil is how you actually do this without, you know, like and get full marks because your explanation's deemed good enough. Well, surely you've got to have the lines x equals a half and y equals a half, and then just say the lattice itself has perfect symmetry. Well, has symmetry. What am I talking? What's perfect symmetry? Has symmetry in the lines x equals a half and y equals a half, which is the center of the circle, as does the circle, as does the circle produced as r grows. So that's kind of nice. Yeah, this implies that meeting a point in one quadrant will, lead to meeting three points corresponding to that point in the other quadrant. Yeah, every time, if you put it like this, every time the circle hits a new point in one corner of the plane, it simultaneously hits the same point after you've reflected in a line x equals a half, then y equals a half, then x equals a half. Equivalent points, simultaneously hits equivalent points in the three other corners. Hopefully that would get me it. I know in the mark scheme they spoke about actually reflective symmetry, like what would be the image of the point x, y after reflecting a line x equals a half and y equals a half. I'm not sure if you definitely need that. Maybe, I don't know. I really don't know. Like I say, I don't consider myself an expert in these papers. This is just my effort at explaining what I would put. I don't even claim it to be perfect by any means, but I put down something like that and hope to get most of the marks, maybe. Okay, part 4. This is interesting because didn't we just prove that when you go from a root 2, root 3 to any pair of integers, it's only got that unique answer? So surely part 4 is just a restatement of part 2. Yeah, because part 4 is saying if your center was root 2, root 3, should we go back to GeoGebra for this? I've closed it, never mind. If you go to root 2, root 3, which isn't right in the middle, you don't have that reflective symmetry anymore, yeah? Because it was very important. I said that, like, as does the circle R, like it's also got reflective symmetry in the line x equals a half, y equals half. Like here, the circle, the circles, well, the reflective symmetry will be like, it won't be, the lattice points aren't symmetrical around that if if you had x equals root 2, y equals root 3. But we've already proved anyway that if you pick any point like AB and root 2, root 3, yeah. Oh, sorry. Let me do it like this. Yeah, the distance. Because this is root 2, root 3, isn't it? That's not AB. Uh, if you had this point as root 2, root 3, it's 1.4 and 1.7, isn't it? I perhaps should have put it a bit higher. But yeah, as this circle grows, it will just hit one point at a time. That's what we proved over here. You can't simultaneously have two distinct points which are the same distance from root 2, root 3. So as that R grows, it will just hit one point at a time. That's what I'm basically going to say. So I'm going to say, well, we know from 2 that, sorry about the handwriting, there is only one point, one integer point, one unique integer point, we should say, that can be a given distance from the point root 2, root 3. That's what we really proved. Yeah, which is interesting. Yeah, so as R grows, and more points fall inside the circle, we increment k by 1 essentially. It's like an inductive proof, really. Yeah, maybe I should say as RO grows, we meet points one by one. One by one. Yeah. Ensuring that k increments through the natural numbers, if you like. Don't skip any numbers or meet two at once. Yeah, I mean, that's what I'm going to say. Would it get me full marks? I really don't know. It's just what I'm going to put down. I always figure, they get an idea of whether the candidate is like, trying to justify themselves and stuff like that. And they might take a couple of marks off if they think, something isn't quite precise enough or they wanted you to say a bit more. It's the kind of way it goes. But, you'll notice what I've tried to do each time is say plenty and convince them I know what I'm talking about. It's all you can do. It's all you can do. I wouldn't, you're only supposed to do these in 22 minutes as well, so I wouldn't write an essay on it. So it's balance. It really is. Anyway, best of luck in the mat. Hope that was useful. Bye bye.